In this chapter, I'm going to talk about indicators and titrations. When you're doing a titration in lab, many of them involve the addition of an indicator to help you determine where the endpoint of the titration is. So a pH indicator is a water-soluble, weak organic acid that changes color as pH changes. So just like the acid or the base that you're titrating, the indicator itself is also a weak acid. So as an example, the indicator phenol red has two different forms. The acidic form is yellow, and the basic form is red. For phenolphthalein, which is the one you use most commonly in lab, the acidic form is colorless, and the basic form is pink. So the pH range over which indicators change color is related to the pKa of the indicator. So remember from the Henderson-Hasselbalch equation, pH equals the pKa plus the log of the concentration of the weak base divided by the weak acid. So since indicators have a weak acid and a weak base form, when there are equal amounts of indicator in the acidic and basic forms, they will be right in the middle of their color change. So one going from yellow to red, right in the middle of that color change would be kind of orange. So since the pKa of phenol red is 8.6, it's going to be a good indicator for titrations that have an endpoint of around 8.6 because a color change will occur between 7.6 and 10.6. So as you can see on this slide, there are many different indicators all changing color over different pH ranges and changing color in different ways. So the one that you're most familiar with is right here, phenolphthalein, which changes color over the pH range between 8 and 10. And you can see a lot of other indicators have different pH ranges over which they change color. So they will be good for different types of titrations where endpoints occur at different pH values. So this slide just gives you a little bit of vocabulary that you should know. So the titrant is the reactant that is added to the titration. So the titrant is the solution that's in your burette. The analyte is the sample. It's the weak acid or the weak base, or maybe the strong acid or strong base that has an unknown concentration. So you're trying to determine the concentration of this compound. So it's going to be in the Erlenmeyer flask. And the equivalence point, the point at which chemically equivalent quantities of acid and base have been mixed. So you've added enough base as the titrant, for example, to react with all of the acid that is in the Erlenmeyer flask. Now at the equivalence point, since there are chemically equivalent quantities of acid and base, the moles of acid that were initially in the flask, so your analyte, have to be the same as the moles of base that were added from the burette. So this equation at the bottom, if we have a volume of acid times a concentration of acid, right, moles per liter times liter, that's going to give moles of acid, and that has to equal the moles of base that are added to the flask. So at the equivalence point, the moles of acid that are in the flask, the moles of analyte, are going to be the same as the moles of base that have been added, or the moles of the titrant that have been added. So let's just do a quick review of titrations. So strong acid, strong base titrations, for example, HCl and NaOH, produce water and salt. And at the equivalence point, the pH is going to be 7 because sodium chloride in this case, the product of HCl and NaOH, that's a neutral salt. Neither sodium plus nor chloride minus react with water, so they're not going to form any H plus or OH minus. So the only reaction that we have at the equivalence point is this one. Okay, acid and base producing water. If we have a strong acid-weak base titration, for example, HCl and NH3 producing water plus ammonium chloride, at the equivalence point, since all we will have left is the acidic salt, right? We've added enough HCl to react with all of the NH3, and that reaction is converting the NH3 into NH4+. So since we only have that in solution, we have an acidic solution. So if we have an acidic solution at the equivalence point, then the pH is going to be less than 7. For a strong base weak acid titration, For example, acetic acid and sodium hydroxide producing water and the acetate ion, or sodium acetate if you want to write it in the aqueous form like this. At the equivalence point, since we only have the basic salt or the basic anion, CH3COO-, since it's basic, then we're going to have a pH at the equivalence point of greater than 7. So again, at the equivalence point, we've added enough sodium hydroxide to react with all of the acetic acid, and the sodium hydroxide is converting the acetic acid into the product. So at the equivalence point, that's all we have left. Since it's basic, then the pH at the equivalence point has to be basic. Now at the midpoint of any titration, the concentration of weak acid equals the concentration of weak base in solution. So that means there is still weak acid and weak base in solution. At the equivalence point, all of the analyte has been reacted. At the midpoint, we have equal amounts of both weak acid and weak base in solution at the same time. And to determine the pH, we use the Henderson-Hasselbalch equation. And at the midpoint, since the concentration of HA equals the concentration of A-, the log of that fraction is 0. So at the midpoint, pH of the solution is going to equal the pKa of the acid. So again, whenever there is a weak acid or a weak base as the analyte, the pH is never going to be 7. It'll either be above 7 if at the equivalence point the only thing remaining is the weak base, or it will be below 7 if at the equivalence point the only compound remaining is the weak acid. And of course, whenever we have a weak acid or base as the analyte, we will have a buffering region, because at some point we're going to have both the acid and the conjugate base in solution at the same time. And when we have that situation, when the concentration of weak acid and weak base are at reasonably high concentrations, that's when we have a buffer. And in that buffering region, a small change in pH occurs over a large change in volume. So if you compare the area circled in blue with the area circled in red near the equivalence point, you can see that near the midpoint or the buffering region, we've added a heck of a lot of solution, say from 2 milliliters to 8 milliliters, but the pH only changed by about 1 pH unit, whereas near the equivalence point, we've added less than 1 milliliter of titrant, and the pH increases several pH units. So the steepest part of the titration curve is where the equivalence point occurs, and before the equivalence point, the flatter portion of the curve is where the buffering region is. And remember, the buffering region only occurs if the analyte is a weak acid or a weak base. So the next couple slides are just giving you an idea of what the titration curves look like if we have strong acid, strong base, or strong acid, weak base titrations. So in this one, we have in the blue, the analyte is sodium hydroxide. We know that because initially we start at a high pH, so it has to be basic, and the addition of HCl results in an ending pH that is much less than 7. And the equivalence point for this particular titration has to be pH 7. Okay, so that's for the strong acid, strong base titration curve. The red titration curve shows a weak base, strong acid titration. We know it's a weak base as the analyte, again, because we start off at a high pH. And notice that the equivalence point in this case is less than 7. So this diagram shows the opposite situation. The red titration curve is a strong acid, strong base titration, where a strong acid is the analyte because we start off at a low pH. And again, the equivalence point for a strong acid, strong base titration is going to be at a pH of 7. And the blue curve is a weak acid, strong base titration curve. We know it's a weak acid because, again, we start off with a low pH. And the equivalence point of this titration curve, shown by the blue dot, is above 7. And also notice both for this diagram and the previous diagram, when the analyte is, in this case, a weak acid, or in the case of the previous slide, a weak base, the midpoint is shown on both of those curves. Okay, so that is a point where the pH of the solution is going to be equal to the pKa of the acid. And notice that that point does not exist on the strong acid, strong base titration curves because there is no buffering region for those titration curves. So when we're choosing an indicator for a titration, the indicator should change color around the equivalence point. So that's the point we want to know. We want to know when the titration is over, so the indicator we choose has to change color near the equivalence point of a titration. So let's just go through a couple of questions, and this first one asks to select an appropriate indicator to detect the equivalence point of a particular titration. So we're titrating a 0.1 molar sodium hypochlorite solution with hydrochloric acid. So how are we going to approach this problem? So the first thing we're going to have to do is figure out what the pH is at the equivalence point of this particular titration. Once we know what the equivalence point is, then we can go back to the previous slide and choose an indicator which changes color near that particular pH. So the first thing we need to do is to figure out what volume of the titrant we need to add in order to get to the equivalence point. And we can use this calculation right here, right? Because we know that the moles of base that are initially present in the solution are going to equal the moles of acid that we have to add. We have a concentration of sodium hypochlorite of 0.1 molar. We know the initial volume of 40 milliliters, and we have the concentration of the HCl. So we can use this particular equation to figure out how much HCl we would need to add to get to the equivalence point, and it ends up being 40 milliliters. You could also be a little bit smart about this question and not even worry about doing this calculation, because as you can see, both the concentration of the sodium hypochlorite and the HCl are both 0.1 molar. So if you have 40 milliliters of a solution of 0.1 molar sodium hypochlorite, then in order to use up all those moles, you would have to add the same volume of HCl, right? Again, because those concentrations are both equal. So now that we know the volume of the equivalence point, now we have to find the pH at the equivalence point. So the reaction I've shown here is the titration reaction. So we have ClO minus plus H plus, right? The ClO minus is the hypochlorite, H plus is the HCl, and that's going to produce HClO. So what we know from our previous calculation here, which I didn't write down, but you can figure this out yourself, is how many moles of base we initially had, and I wrote it down as millimoles. So we have 4 millimoles of base initially present as our analyte, and we've also added 4 millimoles of HCl to react with all of that base. So after that reaction has happened, how much of each of those components is left? Well, since this is a complete reaction, we end up with no ClO minus remaining, no H plus remaining, because that has all been converted to HClO. So now we know that we have 4 millimoles of HClO in solution at the equivalence point. Now this calculation becomes a weak acid calculation. So the next step is to write out the reaction between the weak acid and water. So we have HClO plus water producing ClO minus plus H3O plus. And we know, since H3O plus is produced as a product, that this solution is going to be acidic at the equivalence point. Now, to solve a weak acid problem, we set up an ice table, but we don't have all the information quite yet because what we calculated previously was how many millimoles of HClO we have at the equivalence point, but when we're doing ice tables, we need to have a concentration. So to find concentration, we need a moles per liter calculation. So we already have moles. We can figure out liters because we know how much we started with. Our analyte solution was 40 milliliters. 40 milliliters of HCl was added, so our total volume is now 80 milliliters of solution. So a millimole per milliliter is going to give us a concentration of moles per liter. So now we know that the concentration of HClO is going to be 0.05 molar. So now we can fill out the ice table since we know the concentration. And remember, since water is a pure liquid, we don't need to worry about putting a concentration in for water. So after we fill out the ice table, we continue as normal, using the equilibrium expression to determine the amount of H plus. So we're given a Ka in the question, 2.9 times 10 to the 8. we know that's going to equal x squared over 0.05 minus x. And as usual, since the Ka is small, we can ignore that x. And solving for x, we get a concentration of 3.81 times 10 to the 5 molar H+. So that should be a molar concentration. And if we determine the pH, we end up getting a pH of 4.42. So now we need to find an indicator that will change color around a pH of 4.42. So if we go back to the slide of indicators, and let's just draw a line up from where about 4.2 is. So somewhere around there. It looks like bromocrestal green is a pretty good indicator because it changes color right around 4.2. Now you could probably also get away with methyl orange or methyl red because methyl orange is near the end of its color change, whereas methyl red is near the beginning, but a slightly better choice, because it changes right in the middle of that pH range, would be bromocrestal green. So let's go through one more calculation. In this one, we have the same weak base solution, and we're going to try and determine what the pH is initially. So before we've added any HCl, so just a weak base problem, and then determine what the pH is after 20 milliliters of HCl has been added. So let's just go through this step by step. The first thing to realize is that we have sodium hypochlorite, and we have to determine how that reacts and what its products are. So that is this first equation here. So we have sodium hypochlorite producing sodium plus and ClO minus. Now, which one of those is going to act as an acid or base? Well, we know that sodium plus is a spectator ion, so that's not going to affect the pH at all. And ClO minus, that looks like a weak base. So that is going to be what we use to determine the pH before any HCl has been added. So again, this is just simply a weak base problem. So we're going to set up the ice table. Let's write out the reaction between ClO minus and water. So we have ClO minus plus water producing HClO plus OH minus. And filling out the ice table, we know that we have an initial concentration of 0.1 molar sodium hypochlorite. Since that ionizes completely to produce 0.1 moles of Na plus and 0.1 moles of ClO minus, we know we can start with 0.1 moles of ClO minus. Again, H2O doesn't matter because it's just a pure liquid. And we're going to lose some ClO minus, we're going to gain some product. And at equilibrium, 0.01 minus X for ClO minus and X for both HClO and OH minus. Now, since we have a base, we're going to have to figure out what Kb is. So now we're over here. Okay, we're given Ka. We know Kw equals 1 times 10 to the minus 14, and Kw equals Ka times Kb. So if we rearrange the equation, we can solve for Kb, and we end up getting 3.45 times 10 to the minus 7. So we can use that in our equilibrium expression. So Kb is going to equal the concentration of products over reactants. So it's going to be x squared over 0.1 minus x. And since we have a small kb, we can ignore that x. Solving for x is the same as solving for the concentration of OH minus. So we get 1.86 times 10 to the minus 4. If we take the negative log of that number, that gives us the POH. We're asked to find the pH, so we have to take 14 minus the POH, and that's going to give us a pH of 10.26. That makes sense. We start off with a base, and we should have a pH that is greater than 7. Now the next step is actually fairly simple if you think about it. So we know from our previous calculation, or 2 calculations ago, that it took 40 milliliters of HCl to get us to the equivalence point. In this case, we're adding 20 milliliters, so we're at the exact midpoint of the titration. So we know at the midpoint of a titration, we have equal amounts of HClO and ClO minus in solution. And if we remember from the Henderson-Hasselbalch equation, when we have equal amounts of A minus and HA, then that particular part of the equation is 0. Okay, the log of 1 is 0. So in this case, since we're at the midpoint, the pH is simply going to equal the pKa of the acid. pKa is the negative log of the Ka. We're given the Ka in the question. So the pH in this case is going to equal the pKa, which ends up being 7.53. So that's all I have for this section. As usual, please let me know if you have any questions.